Alright, so in this video, we're going to talk about the equations of motion. Now, I've already made a video before that derived these equations of motions under constant acceleration, and we looked into a more fundamental approach in order to derive those equations. We looked into calculus, we looked into differentiation and integration. In this video, however, now that we know graphs and now that we know how to work with them, and many different characteristics of graphs, like x versus t, v versus t, or a versus t graphs, we will look at those. We will justify a condition for constant acceleration, and using just those graphs, we'll be able to figure out these equations of motions just by looking at them. So this video would therefore be a continuation to the equations of motion, but we will derive them using graphical methods. So in order to do that, I should get rid of this for the moment, and we would start by drawing out our graphs, our v versus t graphs. And through that, we will represent a very general scenario in which a body accelerates under constant acceleration. So the key thing to understand at this point is the fact that these equations of motions, or equations of motion, are valid for constant acceleration. So let me just write that. Their constant acceleration. All right, so these equations of motion that I'm talking about are basically of the form v equals u plus at, s equals ut plus half at square, and the last one being v square equals u square plus 2as. Now, all these are scalars here. The last video that I made regarding these equations, what I introduced them in terms of vectors. I'll write the vectorial representation of them as well. The vectors, in vectors, they become v at a final time t, happens to be v at an initial time of 0, plus a, or the acceleration, times the time. S, which is the displacement vector, happens to be u, which is v of 0 time, times t, plus half a, which is a vector, times t squared. And the last equation transforms as v squared, and this is v squared in the sense of the magnitude square of the vector, happens to be u squared, that's an equal to, plus 2 times a dotted with s. Now, dotted means you have a scalar product there, a dot product there. You need to take two vectors, you need to multiply both their magnitudes and take the cosine of the angles that exist between them. And that would be the dot product of both these, of a and s. So this is the vectorial representation, but remember, our equations of motion pertain to one dimension. These, however, pertain to 2D dimensions, or two-dimensional, or in fact, this actually pertains to 3 dimensions. But we use it for 2D cases and mostly 1D cases. So this is how we usually work with them. 3D rather becomes a bit more involved and more challenging. Nevertheless, these equations here are simply for one-dimensional cases, and since they are one-dimensional cases, we really don't need more directions than 2. So we work with just one of those directions, and we let the negative sign determine whether or not the direction is negative to our convention. And if that happens, then the term, or the scalar here, all these terms here, act as vectors. So these variables therefore represent scalars, and they represent motion in one-dimensional cases, not like these variables there. All right, so with that distinction taken care of, now we can go on to explain how we get these equations just by looking at the graphs. So let's get rid of this. And like I said before, this video will talk about how we can derive these equations from graphs, or graphical methods of deriving these equations, right? So let us have a very general graph that represents constant accelerated motion. So what do we really mean by constant acceleration? If acceleration is constant, then the acceleration is not changing. So if we start with our a versus t graph for constant acceleration, but as it says it is constant, that means that the area under the a versus t graph, whatever it is, would nevertheless denote to the velocities in v versus t. But then again, the more important point is the fact that constant acceleration means that a is a constant value. It could be something like that, and it would hold constant till the point that we are measuring it. So till the point that the motion is constant in constant acceleration, a would be a constant. If a is a constant, that means it could hold a constant value of, say, a naught. Or it could also be a constant in this manner. That is, the motion of the body is like that. It may be accelerated, but with a different acceleration. It could also be negative acceleration, like so. It could also be zero acceleration, all these lines denote constant acceleration. So what's the distinction between all of them? Well, there really isn't. All we care about is the fact that the constant acceleration criteria is held, and this is held in all these cases. So now that we know that the acceleration versus time graph looks something like that, something like this, with a constant a value, a versus t, then we know that if we evaluate the v versus t graph for this situation, then that should look something like that, with a constant slope. So if the slope of the v versus t graph is constant, if the slope is constant, this implies the acceleration is constant. And if the acceleration is constant, then it goes back to that situation right there. So there we have it. We have determined that a velocity versus time graph should look something like that. Continuous increasing velocity at a constant slope. If it is a constant slope, then we know it's constantly accelerated, and that's all that we want to derive these three equations. So let's work with this graph. Let me redraw it once again, just for clarity. So our y-axis right there and our x-axis right there, y denoting velocity, this denoting time. Time is measured in seconds. SEC or S works fine, velocity in meters per second, right there. And as we have figured out, our graph would look something like that. Now you may be wondering, why haven't I drawn the graph from the origin, or for that any other point? It could have been any graph like that. In fact, you could have also drawn a graph originating from the origin. It would really have not changed the dynamics. As long as the slope is constant, it is constantly accelerated. And that is the only criteria that we are concerned with. However, in more general scenarios, it's better to work with a very general case. Now, if you let the graph originate from the origin of the v versus t 2D system, that would have meant that at t equal to 0, the body was at rest. Now, there would be times where we would not want to consider motion right from rest. Maybe we might have wanted to consider motion at an initial speed and would have stopped considering that motion at a final speed, and they may not be at rest. So in those cases, it's really important to work with an arbitrary velocity and do not restrict ourselves to a case where the body starts from rest. It could also start from some other velocity and end at some other velocity, not necessarily at rest. So let's get rid of that dotted line and work with a more general case like that. So what's more general about this? Well, the generality comes in when we assume that the initial velocity of the body was u, and the final velocity over which we consider its motion is v, so right there. So that is to take into account the v and the u that we intend to use in our equations. So we assume that the body initially started at u velocity and u meters per second, say in some direction, like that, u meters per second, and it went on to move and finally culminated in its velocity at v meters per second after the time lapse of t seconds. So this is constant acceleration, and it has always moved with constant acceleration. So this is the kind of motion that we are looking for when we draw the graph like that. So with that in mind, what we can do with this v versus t graph is to evaluate many different concepts. Now, the first thing we look at v versus t is the fact that their slope is constant. The slope of v versus t is a constant. And the reason it's a constant because that is equal to constant acceleration. So we know that acceleration should equal the slope. What else can we figure out from the slopes given the initial and the final velocity and the time that it takes to cover that difference in velocities? Well, the time it takes to cover that velocity difference from u to v is t time. And the slope, therefore, would be this length divided by this length. Now, the height and the base is given by h by b. So you have a tangent of that angle there, and that would be the slope. What is h? Well, h is v minus u. And what about b? Well, b is just the time elapsed, and that is t. So therefore, you have an equation of a equals v minus u by t, or at, if you multiply both the sides by time, at equals v minus u. What you can do is you can add u to both sides to get at plus u equals v. You can invert this equation to get v equals u plus at. Now this is the equation that represents the first equation of equations of motion, which tells you that if you want to know the final velocity and you know the initial velocity and the acceleration and the time, you can just use this formula to evaluate the left-hand side of this equation. So there you have it, v equals u plus at is your first equation. And that came down from evaluating the slope. So with that in hand, what we can do is we can keep that at the back of our heads and work and look into some other properties of this graph. So as we have discussed in our previous videos, if you have a x versus t graph like that, and you can get a v versus t graph from that by evaluating the slope of the x versus t function. If you evaluate the slope of x versus t function, you get v versus t graph. What you can do with v versus t is you can also evaluate the slope of that to finally get an acceleration versus t, which is exactly what we did right now. But there's another way to go around this, and that is in the reverse direction. The reverse direction means, and by that I mean that if you know a versus t, and you evaluate the area under the curve for an a versus t graph, you would get a v versus t graph. And if you do the same thing with v versus t, you would get an x versus t graph. That is, if you evaluate the area between the curve, this curve right there, then you would get the information for an x versus t graph, this. So let's try to evaluate the area of the curve. Now we know that in this situation, the area is positive. So area, or more importantly, the net area happens to be, well, the net area happens to be the area by the white shaded region. Now the white shaded region happens to be a trapezium. The trapezium, because u and v, these line segments are parallel to each other, whereas this line segment in yellow and this line segment, which denotes the time lapse as t seconds, are not. So that means the net area would be the area of the trapezium. Now I'm just going to draw a trapezium in this manner. With that known, what we can do is we can evaluate the area of a trapezium. The area of a trapezium happens to be half times the distance between the parallel lines, which is this, and the distance is nothing but t, multiplied by the sum of the two parallel lines, which is u plus v. So you have u plus v, and that gives you the net area. Well, what about the net area do we know? Well, we know that the net area would take us back to the realm of x versus t. And the only information we know from x versus t is the fact that this is position versus time. So if this is the net area, then this must be equal to the total displacement. And what is the total displacement? Well, the total displacement is given by the variable s. Therefore, the total displacement of s happens to be t by 2 v plus u. So that is how you get another equation. But wait, we don't really have that equation in either of our three equations. What do we do with that? Well, that requires some clever trickery in the sense of substituting one variable for another. So now that we know this piece of information, it's just left to mold this equation to get one of these equations. So let's try to do that with the other equation that we already know. Let's get rid of this. And yes, so we know that v equals u plus at. That's the first equation that we have already derived so far. If we use this in tandem with this equation, we can derive some other relation, which we might hope might be either of the second or the third equations. So let's try to eliminate one variable. We know s equals, well, v plus u by 2 times the time. That can be written as v plus u by 2. And if you substitute for time, you get, from here, you get, well, v minus u by a happens to be time from this equation. Let us substitute this property or definition of time into our original equation that we intend to modify. If you do that, we simply write v minus u by a. So we have the following equation. We have s equals v plus u times v minus u by 2a. Well, you can simplify that by multiplying both hand sides by 2a to get 2, like so, 2as equals v plus u times v minus u. Now, it doesn't take a lot to realize that this is of the form a plus b times a minus b, which is exactly of the form v squared minus u squared. If you do that, you get v squared minus u squared equals 2as. And what does that equation represent? Well, that equation represents the third equation of the form v squared equals u squared plus 2as, or v squared minus u squared is 2as. It simply comes down to adding plus u squared on both the sides to get that equation. So now we have the first and the last equation. We must do something in order to get the second equation. Well, that also comes out from treatment of this equation in a different manner. So, like in the previous case where we substituted for t, let us substitute for some other variable. Let us substitute, say, for v. Let me get rid of this now, and keep in mind that at this point, we have the first and the last equation. So using that, let us mold those equations to get the last one, or the third one, or the second one, sorry. So we know v equals u plus at. We also know, well, s equals t by 2 v plus u. We have also figured out that v squared equals u squared plus 2as. Now it just comes down to using these three equations to get this one, the one drawn in red. So let's choose this equation to work with. S equals t by 2 v plus u. What we do now is eliminate v. The way we do that is to use this information for v and substitute it there. So we have s equals t by 2, and instead of v, we will write u plus at plus u, which is this one right there. So now we have s equals t by 2, 2u, adding these two u's together, plus at. And this comes down to s equals, multiplying the first term, 2u t by 2 plus at squared by 2. Cancels the 2 out, and you're left with s equals ut plus half at squared, or the same as the second equation as well. So there you have it. That is how you would get all the three equations just by looking at the graph. The only thing we did was to use the criteria that we have constant acceleration. We then found the graph of v versus t. We then used the slope to get v equals u plus at, v equals u plus at, and then using that, we used different results out of the other properties of this graph, like area, and we finally got the remaining three equations. Remaining two, I guess. So there you have it. That's how you would draw the graphs, and that's how we would derive these equations of motion. They're very simple, and they're very straightforward, and all that you expected to do is know how the graph would be. The more important point is the fact that graph would be a constant line. And because of that constant slope, or the constant line, we knew that this would be a trapezium, and we were able to derive this equation. And like so, we were able to derive other equations as well. So there you have it. That's how we would work out the equations of motion. So I hope this video helps you. I hope it helps you understand the importance of understanding what the information graphs carry, and how you can use that information to your advantage. So all the best and have fun.